All right, let's start our lecture today. Welcome everyone on to EE5731, I guess. Right. Okay, so first of all, let's discuss about computer vision, which is the topic of today's lecture. Actually the course, which is visual computing or computer vision. And the first question that we want to discuss today is, what is computer vision, right? So as you may already know, that computer vision is about how to make computers work or function like human eyes, basically, to recognize the world through your eyes, through your visual perception. And that's really the goal of computer vision. Given images or videos, we want to know what the contents of these images and videos. And also beyond, not just the same functionalities as our visual perceptions, but we want to go beyond human visual perception. And why is that? What is the reason that we want to go beyond human visual perceptions? Anyone? Anyone can answer these questions? Why we need to go beyond human visual perceptions? Well, what is the problem with human visual perception? Is there any problems with our eyes? You here, is there any problem with your eyes? Well, the first of all is attention. Your attention, your span of attention, your focus is not always 24 hours by 7. You get tired, you get distracted, and you get bored sometimes, and so on. Once you have this, once you cannot focus, when you get bored, when you're distracted, then the functionality of your visual perception will not be to that kind of standard anymore. There's many accidents because human visual perception not focus on what the task is. Right. So beside this, there is a more fundamental problem with this human visual perception. What is the fundamental problem? The limit of the physics of our eyes. What is the limitation of our eyes of physics? Anyone? Visible spectrum. Exactly. So we only limit it to the visible spectrum. And what is the visible spectrum here? Anyone remember in high school? You learn about this, right? The visible wavelengths. What is the band of visible wavelengths? From 400 nanometers or 380 nanometers to 780 nanometers. So this is the visible wavelength that human can see. Beyond this, everything is energy, and this frequency is also energy. But beyond this wavelength of energy, you cannot see it. You cannot see all these spectrums beyond your visible wavelengths. And some animals actually can. For example, dogs can go beyond infrared. So they can go beyond 780 and up to perhaps 1000 nanometers. Bees, for example, they can see ultraviolet. Ultraviolet is a spectrum below 380. So some animals have the capability of seeing beyond the visible spectrum, beyond visible wavelengths. Right. So there's a fundamental physics limiting our visual perception. And in computer vision, we all also want to go beyond these spectrums. All right. So that's the basic idea of computer vision in comparisons with human eyes. Any questions up to this point? Okay, so now the very basic information of computer vision is through input and the output. The input of computer vision is basically visual data, and mainly on the 2D images and videos, but it actually can go beyond 2D images and videos, of course. So everything is 2 dimensions, or 3 dimension in terms of temporal or videos, can be the input for computer vision algorithms. All right, but mainly in this course, we will focus on images and perhaps to some extent videos. That's the input, and the output is visual information. Given images, we want to know what is going on in the images. So that's the basic idea of the in terms of the input and output of computer vision. And these 3 are fields that are not computer visions, but very close to computer visions. The first one is computer graphics, second is image processing, and the third one is AI. Right, so for computer graphics, how many of you know about computer graphics already? Can you raise your hands if you know computer graphics? Okay, maybe some of you, 1 or 2 or 3. I think many of you already know computer graphics, but maybe you haven't learned in the course or taken any course in computer graphics. But the basic idea of computer graphics is that given the mathematical models, in this case, this 3D of 3D information, we want to render image or videos using computer graphics algorithms. So the input here is mathematical model for computer graphics, but the outputs can be images or videos. Right? So the movies that you watch, I'm not sure, maybe in recent years, there's a visual effects in Hollywood movies, for example. All this is the creation of computer graphics. Right? So they create imagery as the output, given some information about the world, in this case, the 3D or the physical parameters of the world. So image rendering is part of computer graphics. And that's the basic concept of computer graphics in comparison with computer vision. In computer visions, it is the other way around. Means that the inputs are images or videos, and the outputs are information, abstract information, or in some extent semantic information. For example, in this case, given the input of this pot here, teapot here, right? So we want to know what is the 3D shape. So we do the inverse process of computer graphics. And we also want to know what is the label of this image. In this case, the object in the image is a teapot. And it is made of wood, meaning that we know the material of the objects. And because there are some highlights, specular highlights on the surface of the teapot, we know that it must be varnished or something that is glossy. Right, so all this information is the outputs of computer vision. Any questions so far for computer graphics and computer vision comparisons? Right. So the next things, aside from computer graphics, we also know about this image processing. In image processing, the inputs is degraded image, like this on the left. Right? So in this case, it's a noisy image, and the output is a clean image. And that's the whole point of image processing. The input is image, and the output is also an image. So from image to image. And that's basically the difference between image processing and computer vision in general. In computer visions, the output is not just an image, but the output is actually some information. Okay. But saying that, actually image processing is a part of computer vision. It is called low-level vision. So in other words, for image processing is low-level vision. So for example, in this case, there is a noisy input image. We transform that into clean image. And from the clean image, we try to extract some information. In this case, the edges of the hands. So again, this is the correlation or the connection between image processing and computer vision. Any questions so far here? All right, so if there's no questions, the next thing is AI or artificial intelligence. I think most of you know that computer vision is part of AI. The difference of AI and computer vision is on this type of the input. AI have all or include all the possible inputs, like in this case, sound, text, signals, even visual data as well. And all this is part of AI. And computer vision is a subset of this AI, because computer vision focuses on the visual information. It doesn't care about a sound, it doesn't care about text, it doesn't care about signals, it only care about visual data. And that's the difference between computer vision and general AI. All right, so I think this is clear here. And why we have to learn about computer visions, right? Well, as you can imagine, computer vision has many, many applications. If you think that your eyes are important, so is computer vision. So not only for robots or self-driving cars, but there are many different applications of this. Like in this case, game technology, biomedical image analysis, computer graphics even. I will show you some example how computer vision is useful for computer graphics. Intelligence vehicle system or intelligence machines for industries. And for us, I hope that I can send or imprint this kind of message that computer vision is challenging, but also very fun. And so that's in the end of the course, you can feel that computer vision is something fun and really, really fun. So this is an application of computer vision. In this case, it's self-driving cars. So I think in the near future, we will have this kind of technology soon in terms of years, perhaps. In your lifetime, we will have this on the street. There are some already on the street now in the US or even in Singapore, and it will be soon everywhere. The main problem why it is not everywhere, one is because of the ethical policy. If there's an accident, for example, who will be responsible? That kind of thing is very hard to answer. And then the second thing is that in terms of the technologies, for example, if you have bad weather, heavy rain, thunderstorm, like here in Singapore, it will be, the algorithm is not yet robust. So if it is rain, heavy rain, for example, then this kind of vehicle at this point of time have to stop because they cannot handle this bad weather. And especially also bad weather in nighttime. And that will be much more severe because you see that everything using camera or LiDAR, but when this LiDAR or camera suffered from raindrops, suffered from rain streaks, for example, then the information will be degraded significantly. And the algorithms, the current algorithms cannot handle all this problem. All right, so that's automatic vehicles. And we know that it's used in surveillance. It's already used actually in surveillance. Right. It's not a good, nice thing, but it's for some positive side. It is useful also for us because it can make our society more secure. All right, so another thing is human-computer interaction. So at the moment, the very basic things about computers, when you interact with computers, you always use keyboards or mouse at least, or maybe in your mobile phone, you use your screen to touch and so on. Keyboard, for example, have been there with us for many, many, many years, and we still use keyboards. So the dream here is that in the future, we don't want to use keyboard anymore because that's not natural. When we interact with other people, we don't use keyboards to talk unless you are in a certain distance, right? But when you communicate with other people, you communicate verbally and you communicate through your gestures and so on. So we want to have this kind of interaction, natural interaction, also with computers in the future. And that kind of interaction requires computer vision technologies. Right, so that's for HCI, human-computer interaction, and this one is an example how computer vision can be useful for computer graphics. So in computer graphics, as I mentioned again, the input is the model, the 3D mathematical model or physical parameters, and the output will be images. So now the question is, how we can get these 3D models in the first place? How can we know the parameters of certain objects? the physical parameters of certain objects. So these parameters, the 3D, the physical parameters, can be obtained by computer vision technology. So first you capture the objects, and then you extract the 3D or the parameters of the surface reflection, and then you use that information to generate different types of objects. So that's the idea of how computer vision can be useful for computer graphics. Okay, so let me pause here. Any questions so far? Okay, so there's no question. Let's move on. This is another kind of HCI applications in game technology. So in this case, Kinect is actually a computer vision application. Although it's a bit old now, a few years ago already. But if you know about computer visions, you know the technologies of many different applications, many different domains. All right, this is obvious that computer vision is useful for robots. And yeah, there are many different applications of computer visions, and I think that's the reasons why you are here, why you're interested in this course, because you know that there are many applications of computer visions. And there are many aspects also in computer vision. Computer vision is not just one field. Computer vision is actually applied science. So it is applied mathematics, it's applied optics, and it's also something to do with machine learning. So we will learn a lot about machine learning also in this course. It's not only just computer vision, basic information about the domain of computer vision, but we will touch on some techniques in machine learning. So other boost is something that we will learn. Classification is something that we will learn. And graphical models, not computer graphics, but graphical models is a concept of graph connections between different information will be learned as well in this course. So there are many different aspects in computer vision, and we will learn some of them. And in the end, up to the end of this course, we will learn about optimization as well to some extent, right? Okay, so now why computer vision is difficult? Computer vision is difficult is because one of the reasons is because of this. This is the label. If you search on Google, chair, right? When you search chair on Google image, this is what you get. There are many different things in terms of the shape, in terms of the color, in terms of the appearance, but all of them are called chairs. Something that even for this one is called chair. Something like this one is called chair. Even table is also can be called chair sometimes. So not only shape, not only appearance, not only color, not only functionality, but somehow the combination of all these can be called chair. And this kind of notation of chair is man-made term. Man-made terms mean that we create this kind of word, we create this kind of label. And for computer to know and understand our term is difficult. So we need to supply a lot of different images for computer to learn what we call chair. Right? So that's definition here of an object is a big problem in computer vision. So this is called object variations. So with one label, but many different kind of meanings. Any questions so far here? Right, so another problem in computer vision, aside from the possible shapes and appearance, is lighting. So in this case, you see that I think if you have a normal eyes, you can see that a picture of man and actually the identity of the man are the same. Right? This is the same person, but under different lighting. For human eyes, because we are trained so well in this kind of situations, we know immediately they are the same person. But for computer to know this is very difficult. Why is that? Because as you can see here, for example, in the forehead of this person, when we talk about computer vision, we talk about image. And when we talk about images, we talk about pixels and pixel values. And pixel values is actually intensity from 0 to 255. All these actually numbers. What you see in your eyes actually also numbers. Right? So the same in computer vision, the input image here are all numbers. And the numbers here in the forehead is very high value, close to 200. But then if you compare with this one, the same forehead, because it's so dark, the intensity value of the pixel is so low, it's close to 0. So now how you can infer the same thing from very different values? One is 200 kind of intensity in some region, and the other is 0 values in the other image. How can they be the same? So from computer perspective, it's very difficult to judge. It's not something easy. So that's why the lighting condition is another problem in computer vision. And this is something that interesting. This is called color constancy. Human has this effects of what is we call color constancy. So if I can ask you, what is the light color for this image on the left here? What is the light color? Anyone can guess what is the light color for this image here on the left? It's yellow. I think if you have a normal eyes, you will say that it's yellow, right? So that's actually your capability to estimate light. It is automatic in your brain that it is yellow there. And this capability is called color constancy. Even though the lighting colors are different, you can still see that same color, somehow the same color. Although you know that the color is different, for example, grass. In the morning, when the sun is rising, and in the afternoon, when the sun is on the top of of your head, the color of the grass, the same grass, actually different. But for you, for your eyes, they are actually the same green. So it seems for your brain, your brain can discount the color of the light automatically. And this is useful for your survival. So that's why it is there in your brain. So I give you an example here. Now, let's see. So for this one, the region here or the patch here, the chips here, right? What is the color of this region here? Blue. How many of you say blue? Can you raise your hand if it is blue? All right. Thank you. How many of you say that it is not blue? Can you raise your hand? It is not blue. Well, the answer is that it is not blue. It is not blue. Why? So let's see. I will crop this one. You see my process here is just cropping this one, right? I crop this. So that's the color actually. Oops. Yeah, I just cropped that, right? So this is the color. What is this? Gray. It's nothing to do with blue at all. So what happened with your brain then? Your brain says that's blue, but it's actually not. It is gray. So this is something that is much more difficult for computer vision. Why? Because the data that you receive is different from the data that you interpret. Your data that you receive is literally gray. But your brain manipulates that grayness, change that grayness to become blue. Right? So your consciousness is not always based on the reality. Again, your consciousness is not always based on reality. So be careful with that. So when you make a judgment, be careful, because your consciousness, what you think is true, is not based on reality. Right? So this one is the case that we have some other process there in the brain that changes the color automatically for you. And again, this is called color constancy. There's a process, computational process in your brain that transforms this one. Why is that? Why gray become blue? Any idea? Why the gray become blue? Because of the yellow light. You know that the light is yellow. Your brain knows that the light is yellow. So that's why it's convert the gray to blue, because otherwise you will not survive. I mean, your ancestor will not survive and you will not be here, right? Because it will not be able to differentiate between lions and grass. Right? So that's the problem. So that's why it is embedded in your brain. Now, that's well, they just show here that actually they are gray. The blue parts are actually gray. And the red part here is actually orange. Now, that's when your light is yellow. But when your light is blue, now the light here is blue, you know that its light is bluish. When the light is blue, the blue is actually, the red is actually no longer red, but it's purple. The purple here. And yellow is actually not yellow, it's actually gray. The same gray as your blue. Right? So yeah, your brain has something. It's not just taking whatever the things in the world. Any questions here? All right. So you get my point here, right? It is difficult for computer vision algorithms to know this. And secondly, your brain has some computational process. I cannot put this on because there is no space for the fun. Right. So this is another example that your brain actually manipulating the data. So now A and B, who's saying that A is darker than B? Who think that A is darker than B? Can you raise your hands? Okay, some of you, because you already anticipate that there will be some illusion here. Okay, that's fine. Who thinks that B is actually darker than A? All right. Anyone think about other things between A and B? Yeah, they are equal. They are actually the same brightness. So if I put the three things there, you see now that A and B are the same brightness. They're actually exactly the same image. I just put that kind of things there. Right? So this is the way your brain manipulating the data. Why? Why is that? Why your brain manipulate the data? Because of the shadow. Because you know that the shadow is on B, then your brain say that B is under shadow and thus it have to be brighter than A. Again, this is very important for your survival, the survival of your ancestors. So that's why it's embedded in your brain. Any questions here so far? Okay, so another illusion is called size constancy. So here I think most of us know that the man there is actually the same size or maybe even taller than the lady. But when we change the perspective, we change in this way, for example, then we see that the man it become dwarf, right? Become mini man. Why is that? Why is this? What is the cause of this? It's called perspective, right? We know the depth, and because we know the depth, and the first image here on the left, we know the depth that the man is far away, and because we know that the man far away, then it should be the same size as the lady. But on the other image, we lose the sense of the depth for the man. And that's why we force ourselves that the man must be mini man, a dwarf man, because there is no depth that helps him that help us to know the actual information. Again, this is called size constancy, and that's also embedded in our brain that we include or we consider the depth in our judgment. Oh, by the way, all this is really part of our consciousness. We don't really even think about this. It just happened that we immediately know. So that's why it is called consciousness. You immediately know that the man is the same size as the lady for the left image. This is another example, right? So this one, they focus on the circle in the middle, and this one, right? So again, it's focused on the circle in the middle, and in the circle of the middle, actually the same size from the left and the right image. But then from the right one, it seems that it's smaller than from the left, right? Because we take into account the surrounding, we take into account the context of the objects. And again, this is also embedded in our brain. We take into consideration the relativeness of the shape with respect to the surrounding. Right. So this, I think, is the last example of the optical illusion here. How many of you see a dog? There is a dog there in the image. How many of you notice there is a dog? Only 3 of you? We are more, I think, yeah. So many people actually already raised their hand. Actually, there is a dog, a Dalmatian dog, right? And this one is the ear of the dog, and this is the head of the dog. This is the collar of the dog, and this is the mouth of the dog munching on the grass. Okay, and this is the tail of the dog is around here. So again, this is the head of the dog is here. Can you see that? All right. Well, if you cannot see, just I will share this slide with you, and you can see at home and find the dog there. Okay. So now, why human can see the dog there? Many of you actually see the dog there. Why is that? It's because we can find patterns. So patterns identification is very important for human as well. Right? And in this case, for computer to understand that the patterns, there is a dog patterns there, is very difficult. Humans so good in finding patterns, especially two-dimensional patterns. And computer vision now, the technology try to keep up with this capability to find patterns. All right, so another problem, this is not an illusion, but it's a fact, that light source, you see that when you see this room, for example, for you, it's immediately you understand what's going on. There are some people, there's some light here and there. But if you think about this information as a light rays, because this is actually light rays, right? The light is coming from the top of the light and the top of the overhead here, and then they will go into a certain surface. So like this one, for example, there is a one light source exhibiting or emanating the light in all directions. So emitting all the light in all directions. And one of them go to one surface point here. Okay. Right, so we have a light source emitting the light rays in all directions, and one of the direction go to this surface point here, and from that surface point, which is called diffuse reflection, it will reflect the light into all directions. So from this point, it's in all directions as well. And one of these will go into this point, and then it's also emitting the light in all directions, which is called reflection, right? So in this case, it's called interreflection. Right? So we have reflection in one point here to be reflected in the other point, and from this point is reflected into the other point, and so on and so forth. So if you trace the light rays, it's very, very complex. So when you see this scene in this room, as very simple because you immediately understand what's going on, actually it's very, very complex. because the light is bouncing here and then bouncing to the wall, bouncing to the other wall, bouncing to you, and so on and so forth. So all the light process here, the bounce of this light is very complex, but it's a rich of information. So the light, actually the rays here, working around us here, carries some information, and very important information actually. And that information is also something that we want to capture in computer vision. Okay. All right, so now, as I mentioned again, this is an image that I think you immediately know what's going on. In a fraction of a second, you know what's going on there. And again, this is called consciousness, right? So the imagery of this image suddenly in your brain, and you can understand what's going on there. Now, we know that this one is American football, I think. If you know American football, you immediately notice the pattern there. In the middle, there's some players, and the surrounding here are spectators, presumably human spectators, right? Now, if you look at this guy here, I think it's a guy. I'm not really sure if this. I think it's a guy, not really a girl, right? It seems to me like that. So look at this person here. Which direction that this person looking at? Looking at that direction or the other direction? Left direction or the right direction that he's looking? Right there, right? Right and your right. Right. So somehow we know the direction of the person is looking at, but we want to know whether this is true or not, right? Is it true? Now, to answer that questions, we don't have any other information except this image. This is the only information that we have. This is the only data that we have. And we want to verify whether this is true or not. How we can do the verification? If it is the only image that you have, you zoom in, right? You zoom in for that particular region to make sure that this is looking at that direction. Let's zoom in, because zooming means that we still use the same data. We just zoom in into that data, right? So if you zoom in, that's what you have. You don't even know that it's a person or not, let alone that the gender of the person. You don't even know the direction anymore. What's going on here? This is actually the data that you have, the data that comes to your eyes. But your brain again do something beyond the data. And that makes computer vision is very difficult. Because we have to go beyond data to infer the information. So that's keep in mind that one, that we have to infer something beyond the data. And that's one is the case of this region of this person here. Let's look at the other region there. What are there? What are these regions here? Presumably humans, right? Presumably they're humans. If we zoom in, we hope that we can see the head. And if you zoom in, that's what you get. It's very, very, very noisy image. So, but we didn't realize this in the beginning. We didn't realize that in the beginning, that it's so complex. We just presume that we understand the whole thing is there for granted, immediately in your consciousness. But again, there are a lot of things going on in your brain, even for this kind of simple image. So you so-called simple image here. And that's something actually that make computer vision interesting. We might not be able to go up to this point to solve this problem, because this problem is actually still somehow an open problem. But we will try to learn about the basic of computer vision algorithms in this course. All right, so yeah, so basically this is why computer vision is challenging, and try to solve this problem is very fun, especially if you look at the information that we have as the input. Again, it's not only just something imagery, something like like this one, but they are actually numbers, right? We just play with numbers in computer vision. And these numbers is not only just for discrete numbers like in the case of computers in this case, but also for your brain. Your brain actually are processing these numbers in terms of signals. Signals are basically numbers, more analog numbers, but they are actually can be represented by numbers. Yeah, so this is the input. This is the reality that we have to face, that the input are all numbers, and how we can make sense that this is a head of humans based on these numbers. Okay, so that will be the first thing that we will learn today, hopefully, in the subject of face detection. So we will learn soon later on how we can detect faces. Okay, so in computer vision, there are a lot of different algorithms, but I can categorize them into 4 different kind of tasks. The first one is recognition, which we will learn soon. Recognition here is object recognition, face recognition, any kind of recognition. It is called also localization, and sometimes it's called segmentation as well. But this is the whole thing is about recognition. It's a higher level computer vision. Okay. And the second topic that we will learn in this course is 3D reconstruction. Given in images, how we can know the depth, how we can know something is far away, something is nearby. We will do the reconstruction when we discuss about the 3D reconstruction. And after that, around 3D reconstruction, I think will begin around the recess week. So after that, 1 week or 2 after recess week, we will learn about motion analysis. And motion analysis here means that we want to know the direction and the speed of an object. So this will be a video-based kind of analysis. Given a sequence of images, we want to know what is the direction and the speed of an object in the video. And the last thing is low-level vision. Low-level vision, as I mentioned again, is the same thing as image processing. So how we can remove noise, for example, then we will, if we have time, we will learn a bit about this low-level vision. So this is the 4 topics, the 4 main topics in computer vision. Any questions so far? Okay, so let's move on the logistics. So this is something that you need to pay attention to because this will bind you in this course. The first thing is the assessment. The first thing is the assessment. The assessment consists of assignment or CAs and final exam. The CAs will take 60% and the final exam will be 40%. Okay, so there is a heavy focus on the assignments because, as I mentioned again, computer vision is an applied science. So you need to do something in terms of the implementation. Okay, and the theory will take up 40%. Any question on the assessments here? Right, that's a good question. How many assignments? So there will be 2 assignments. I think 2 assignments. First is in the first half and the second one in the second half. Right. But as you can see here, assignment is 60%. Means that the assignment will be heavy. In terms of the programming will be heavy. Because it's up to 60%. Normally, in other courses, you will see that the final exam is 60%. But not in this course. Means that you have to spend more time on your assignments. Any questions? Any other questions? Yeah. Sorry? Oh, there's midterms. So there is no midterms. Only final exam. This is a graduate course, so we don't have midterms normally in the graduate course. Any other questions? Yes. Individual, unfortunately. Yes.
So each assignment takes up 30%.
30%, that's correct. Yeah, 30% for each of the assignments. Any other questions? Yeah. Will there be a programming in the final exam? A good questions. The answer is yes and no, means that, algorithm is the key of this course. Means that you have to know algorithms. And the algorithm can be written in pseudocode. It's not necessary to be in the language of certain programming language. So that's why it's not really programming language kind of exam questions, but it will be in pseudocode algorithmic kind of questions, algorithms kind of questions. Yeah, and yes.
So is a paper-based exam not?
That's another good question. So the whole things about the course will be face-to-face. There will be no online or anything except the government change the policy, right? So in that case, even the final exam is planned to be face-to-face. And the mode of the exam, we haven't decided yet, to be honest with you, but it's likely that because of the number of the student here is almost actually exceed 100, it's likely that it will be multiple responses instead of essay, instead of direct answers. All right, but again, we haven't decided yet. Any other questions about the assessments? Right. Okay, so the assignments, programming language will be Python. And the library is OpenCV if you want. It's not really compulsory, but OpenCV will help you a lot. And well, sorry, there's no PyTorch. No PyTorch in this course. So there will be no PyTorch. Sorry for that one. So remove PyTorch from the slide. There's no PyTorch because this is not. There's nothing on in the topics of deep learning. So we will not learn anything about deep learning. Why? Because we want to learn about some fundamental techniques in computer vision. So if I teach you deep learning in this course, you will not understand what's going on there because everything will be black box, right? So we will learn about something that is not black box. So no PyTorch, only OpenCV. If you want, you can use OpenCV. For some function, so from high-level function, you will not allow to use OpenCV functions. Okay, so if you're not sure, you have to ask us, me or the GAs, whether it is allowed to use certain function, because OpenCV is so big that it captures many different functions already. And if you use the function there, you will not learn anything. Okay, so the working environment will be Jupyter Notebook. So how many of you do not know Jupyter Notebook? Do not know Jupyter Notebook? Oh, okay, so a few of you. Unfortunately, you have to learn. It's very simple thing. It's like Microsoft Word, but it's a bit different, of course. The good things about Jupyter Notebook is that what you compile and what you submit will be exactly the same. I can just see the compilation results there on the Jupyter Notebook. Right? So this is to make sure what you get in your experiments is also something that I receive. Okay, so if you cannot compile or you cannot get any results, that will be reflected in your submission because you use Jupyter Notebook. Any questions about these requirements of Jupyter Notebook? Again, Jupyter Notebook is very simple things. You can just learn 5-10 minutes about Jupyter Notebook. Yes.
Does that mean we have to submit a program with IPyNP?
Yes, IPyNP. That's correct. So the extension IPyNP is the extension of Jupyter Notebook, and that file is something that you need to submit along other files that is needed. The main thing is that we have to be able to compile your submission. Yes.
Will there be any skeleton code, or we have to start from scratch?
You need to start from scratch. Yes. But there are GAs here, and the GAs will help you. So look at Luminous to know the email address or the email addresses of the GAs. So we have 2 GAs. One is Jeremy and the other is Xin Yuan. Okay, so there are two GAs that can help you with your assignments. If you have any problem with your assignments, contact the GA. Okay, submission is through Luminous and the deadline are strict. So late submission will be deducted 2 points for every 24 hours. All right, any questions here so far? Okay, so the course website where I put the lecture notes and reading materials on this course website here. The easiest way is to remember that link, right? Or you can also just search on Google. Normally that's what I did because that will be easier. So basically just search my name and then look at the teaching and then use visual computing, and that's the course website. Okay, so I will populate whatever here. So at the moment, there's an additional resources. There will be a reading material as well, and then will be some lecture note here. The slides and the lecture note will be provided as well in this website. So on Luminous, you can also find the link to my website, to this website. Okay. Any questions so far? Yes. Yeah, that's a good question there. The problem with that is that normally when I prepare a few hours before the lectures, I will immediately change. So my worry is that if I share it with you, then it will be not the updated one. And there will be so many different versions. And that will confuse you, which one is actually the official version that is updated. So to prevent from that, I just release right after the lectures. And also, you will pay more attention in the lecture, in the classroom, when you don't have something that can distract you. So I hope that's will be helpful. And of course, saying that, if you look at the internet, for example, and type EE5731 lecture notes, then there will be a lot of information on the internet. But that will be not official. I might change the lecture notes. But if you don't, if you think that the lecture note is useful for you before attending the class, that's the information. Just search on Google EE5731 lecture note. Okay. This is the important things about assessment, which is academic honesty. So exchanging codes is not allowed. You can discuss with your friends, okay? You can discuss with your classmates, but exchanging code, copy and paste the code from each other are not allowed. You have to write your own code. It will be detected automatically by software, so be careful with that. Okay, so even if there's a code online, you have to be careful. You have to mention the reference where you take that code. Okay, otherwise, you will be detected, and then you will be assumed to cheat on your submission. Okay, so if you copy something from the internet, please put reference properly. And of course, it cannot be 100% copy and paste from that reference, because it's, doesn't make sense that it's your work, because it is actually have to be your work that have to be submitted. So please follow this academic honesty strictly, especially for the final exam. Last year, there are a few cases that the students cheated and they get expelled. It's not worth it. Really, it's not worth it. You get expelled in the end. Some of the students are very bright, some of them very, very good, but because of these things, they got expelled. So please don't do any cheating or academic dishonesty for your assignments and for your final exam. Again, the punishment is very, very severe. All right. Okay, so for the reference, there are a few textbooks, but I will not use the textbooks very, very strictly. It will be used loosely. But you need to have this textbook so then you can learn something. Sorry, again, the deep learning thing you have to remove. I forgot to remove this deep learning thing. So remove this one. I will revise this and then share with you. So there is no deep learning. Computer vision is used. And again, you have to look at the course website. The course website here for any reading information. So I will populate here the information for the reading material. And basically, I will use mainly these two textbooks. One is computer vision, learning and inference. And the other is when we talk about geometry, depth information, then I will use multiple view geometry. Okay, so any questions so far? So for state-of-the-art information, state-of-the-art techniques will not be covered in this course. We only discuss the fundamentals in computer vision. We will not discuss any state-of-the-art computer visions. And if you want to know the state-of-the-art, you can just look at this publication in these venues. The publication in these venues like CVPR, ICCP, ECCP, TPAMI, and so on. And actually, there is a course on deep learning. So if you are interested in deep learning, just take that course. Again, this course will not discuss anything in deep learning. Any questions here? Right. So again, I will share this slide with you. And actually, I recorded this lectures as well. So I will share the recording as well. And right. So if there's no questions, let's move on to the topics of image formation. Again, are there any questions about logistics before we move on? Okay, so if there's no questions, let's take a look at this image formation. So in image formation, basically, this is something that we want to learn. We have the 3D world, and we have the 2D images. And we want to understand what is the process in between. Well, the process here means that we have to understand to some extent how cameras work. Right? So let's focus on the cameras here, that the process which is called image formation, from the world to images. And in this image formation by the cameras, there are two fundamental aspects. One is geometry, and the other is radiometry. Okay, we will not look at the geometric aspect this time. It will be learned later on when we discuss about 3D reconstruction. But the fundamental things about the geometric perspective is that an image in 3D will be projected on 2D. So this one is a 3D world here, and it will be projected onto 2D plane. And the basic things about camera, even for the current camera technologies, I mean, follow the pinhole camera. The basic idea of the pinhole camera is that you have this chamber, duct chamber, and then you have a pinhole here, and the rays from outside will enter this hole and project an image on the wall. Okay, so if you look at the link here, oops, right. So if you look at this link here on YouTube, this is how people do the projection. So I think you know already about this. I just want to make sure that you understand what I'm talking about. So here, people have a room, and then they put something, black curtain or black cover on the windows, and then they create a hole, right? And then based on that hole, there will be a creation of imagery on the wall. So I think you know about this when you're young, right? So that's what we means by pinhole. So we project whatever the 3D into 2D. Right. So that's the idea of the basic idea is the same. Even for the current cameras, the very high-end cameras still have the same mechanism. And the pinhole camera system will influence the quality. So I mean, the size of the hole will influence the quality. If you increase the size, it means that more energy coming to your room, to your chamber. It means that it will be brighter. But it also create a blurriness because it will not focus that much. Now, if you want to really focus the sharp edge of your image on the wall, then you have to reduce the size of the hole. If the size of the hole is so small, the image, the sharpness of your image will be there. But your intensity of the image will be much lower, means it's a bit dimmer or darker compared to the bigger holes. So this is the example. So if you use small holes and wait for sometimes, it can be sharp and bright, right? But if you have a big hole, it will be blurry, something like on the right. Okay, and it is actually brighter some on the right. So that's the idea of pinhole, or in the modern terms, it is called aperture. So in your modern cameras, there's an aperture as well. So if you set your aperture large, it means that it will be very bright. But if you set the aperture very small, then it will be dimmer but sharper. Okay. All right. So now in modern cameras, we don't use explicit holes anymore. Of course, the concept is still pinhole, but there's the idea is not really rely on the hole anymore. The idea is to rely much more on the lens. So why lens is so important in the modern camera technology? Because using lens, we can have more intensity. So in the pinhole system, one point in the wall represented by one ray. So one light ray will hit into the wall, and that is the value of your intensity based on only on one ray. But using lens, as you can see here, for this point here, for example, the tip of the pencil here, it is not only receive the ray from the direct ray here, but also receive many different rays from many different directions from the same tip of the point there. So that's why using lens, you can accumulate more lights. And if you accumulate more lights, then it will be brighter immediately. You don't really need to wait for a long time to make it brighter. Right? So that's how lens can be useful here to make your image brighter immediately. And this is the example. If you use a pinhole, it will be very dim, but if you use a camera system, lens system, it will be much brighter. Any questions so far here? So this is very basic. If you are in photography, then you know all of this. Okay, so now in terms of the geometric aspect of computer vision or geometric aspect of image formation, this is something that we want to ask. Given a point in the 3D world, this ray of light will come to the camera, and the camera will generate an image here. Of course, the image is inside the camera, not outside the camera. But here is called virtual plane, virtual image plane. That's why I put the virtual image plane outside the camera. So that's something that we will use later on, which is called, again, virtual image plane. And if we have this virtual image plane, which is the image itself, then we ask, what is the correlation between this 3D point and this 2D point? Basically, there are three components here. What is the correlation between this point and the camera with that point into the image? And this kind of correlation will be learned in the geometric 3D reconstruction. Okay, right. So we will discuss this later on. The second aspect is a radiometric aspect, and radiometric aspect means that we want to know the value of your pixel intensity. So when you have an image and then you use any editors like Paintbrush or Photoshop, when you put your mouse on certain pixels, then you will know the value of that intensity, right? Whether the intensity is 0 or 5 or 10 or 100 or 255. So the value of 0 to 55 is called pixel value. And the radiometric aspect here asks a question, what is the meaning of that? What is the meaning of this pixel intensity value, right? So basically, this pixel intensity value represents light, the energy. And for that reason, we have to know what is light, what is energy, and also what is a pixel value, what is it represents for, right? And how does the camera can transform light into a pixel value? How the light, the energy here that we receive, can be translated into numbers, into pixel value numbers. That's a question that we want to answer here in the radiometric aspect. It's nothing to do with geometry. It's something to do with the pixel values. Right, so light is actually electromagnetic radiations. So basically light is wave. So that's why we talk about wavelength, spectrum. And all this is because light is a wave. So when I say light rays, there's a confusion there because light rays implies that light is a photon, right? Light is just a point that traveling through space. So that's why it's called light ray. But at the same time, this light ray is also a wave, right? So there's a duality here of the light. Light can be a photon, can be a particle. Particle here means photon. And at the same time, it's also a wave. So the particles, somehow, we do not understand yet, can also behave like a wave. And this is called wave-particle duality of light. So in this course, sometimes if we discuss about camera sensitivity, for example, later on you will understand what camera sensitivity is, we will talk about wave, right? But later on, when we talk about light rays, we just assume that the light is just particles, no longer a wave. Okay, so please differentiate between these two notions, that light can be wave and the same light can be a particle. All right, any questions here? Okay, so in terms of the waves, of course, if it is wave, then you have a wavelength. Because a wave means that you have a wave and then the wave have a length, right, between the two tips of the wave. And that kind of distance is called wavelength. So this one has a small wavelength and this one is a high wavelength. And of course, wavelength here is the inverse of frequency. Higher wavelength means a small frequency. And as we discussed earlier, in terms of the energy, light is energy. And in terms of the energy, light can have a frequency very, very high. It means that a very, very short wavelength. This one is very, very short wavelength, which is gamma rays. And light can also have very high frequency. Low frequency means that it can be very high in terms of the wavelengths. So the high in terms of wavelengths here can be radio wave. So radio wave of television waves or television energy or signals are actually the same light that we have here. They are the same thing, the same energy. But why we cannot see the light, the signals of the TV or the signal of the radio? Because they are beyond our visible wavelength. Right? So in terms of the visible wavelength, we have this 380 nanometers until 780 nanometers. And beyond that, on the left is the ultraviolet, and on the right is called infrared. But all this, again, in computer vision, mostly we talk about visible wavelength, but it's not necessary to be in that way. We can also use ultraviolet and infrared. So that's why in the modern camera, if you have a mobile phone, some mobile phones have infrared and even ultraviolet because they want to capture more information, basically. And in infrared, for example, is very good or very useful for nighttime or low light conditions. Right? So that's why it is more useful to capture something beyond visible wavelength as well, not just focus on visible wavelength. Right, any questions so far here? Okay, so if there's no question, let's move on. Because it's a wavelength, so the light that you have here is to have some distributions. Some distribution means that assume that you have a tungsten lamp. Tungsten is something like, we don't have tungsten here. In the old house, when you have a red light bulb, the bulb is normally a tungsten lamp, and the tungsten lamp is actually reddish kind of light. And reddish of light means that in the high wavelength is very high, in the low band of wavelength is very low. This low band of wavelength is a bluish kind of energy, and this is a reddish kind of energy. And that's why the tungsten lamp or bulb lamp that you have at home is reddish, because the distribution of the spectrum is more high in the red side than in the blue side. That is for tungsten. For the sun, for example, at noon, at 12 o'clock, it looks like a white light for you, right? And actually that white light is because the distribution of the sunlight is actually somehow the same for all bands. So for all bands here, the sunlight here almost the same. Although there is some high energy in the green side, actually in the blue side and the red side is not that low. That's why the sunlight at noon look like white. Okay, so that's the reasons here from the perspective of the wavelengths. And for fluorescence here is a neon kind of light. We don't have neon kind of light. Maybe this kind of neon of light, I think. If you look up at that lamp, it looks like whitish kind of a color, right? The reason is because if you look at the blue line here, the blue line here is mercury vapor lamp, which is a neon light. And that's why the reason that is somehow whitish, because the distribution across the different spectrums are almost the same, except a few spikes here. But this few spike is so small that we don't really even see it. Right? Why we don't see it? I will explain that later, because we only have RGB, red, green, and blue channels. Anyway, so that's the idea. So we have a light, the radiation, the energy coming to the camera, and the camera convert the energy into numbers. Now the question is how this energy signals becomes numbers. And the reason is because of CMOS or CCD. And on top of that, we also have color filters. So these two, CMOS, CCD, and color filters, play important role in converting the numbers and converting the energy into numbers. Right? So how the energy can be converted into numbers? The idea is CCD is a receptor. So the receptor is very sensitive to the light. When the light coming, which is in this case a photon, particles coming, it's like a bucket. If you have a bucket at home and then the bucket receives raindrops, for example, for each drop, it will be stored in the bucket. It's the same thing. So we have a bucket here, and the bucket here is in terms of the receptors, or CCD in this case. And the CCD will be sensitive to the photon or the particles and store this energy inside the CCD. And depending on how many photon or particle received by the receptors, then that will be counted, will be convert into the heat or voltage of the system. And this voltage here can be represented by numbers. Right? So that's the basic idea of how this conversion is going on. Now, like many devices, this receptor here or CCD has some sensitivities. So most of this CCD is very sensitive in the middle of this wavelength. So it's very good in receiving the energy of the particles in 600 or 700 nanometers. But it's very bad in the other bands like 400 or 800 here. So that's why if your energy happens to be in this band, the receptor will take the energy quite efficiently. But if the light or the energy is in the infrared, for example, then the sensitivity of this CCD will not be that much. Means what? Means that the image that you will have for the infrared will be much darker than the image that you have in the visible wavelength for this type of sensitivities. And of course, some device will have more sensitivities in the infrared. So this depends on how you design the receptor. Okay. Any question here for the CCD sensitivity? And again, this is called spectral sensitivity. So your CCD, your camera, is also depends on the device, on how they can capture the light. Even though the light is very flat, assume that the light is very flat, it's not necessary that it will be the energy will be taken equally for different bands. Okay. Again, any questions here? If not, then let's move on. That's how we convert the energy into intensity, into grayscale pixels. But now, if you look at your pixels, actually you have 3 channels, R, G, and B, right? So how we can have R, G, and B from grayscale value? So here is only grayscale. The previous one is only grayscale. So the previous one here is only grayscale, only one channel. So now how we can have 3 channels from this one channel information? So the answer is because of the color filters. We have filters R, G, and B. So in the past, in the long past, we have this called rotating wheels or color wheels. So when we have an object here, the wheel will try to rotate bit by bit to get RGB values. As you can imagine here, what is the drawback then? What is the problem here? Very slow, yes. The rotating wheel will be too slow for the object that move fast. If the object is move fast and then the rotating is not there, then the RGB value will be representing different objects. Right? So that's why this is not efficient, this rotating wheel. We don't use this anymore in the modern cameras. So another idea is using beam splitter. So beam splitter means that you have a light here, one ray of light, and then you have this splitting, beam splitting. So beam splitting only pass a certain band and reflect the other band. So in this case, it reflects the green channel, the green band wavelength, and then transmit that into the green one here, the green receptors, and then pass on the red receptor to the red receptors, and then reflect here to the blue receptors or blue CCD. In this case, we will have RGB as well. But what is the problem with this? What is the problem with this beam splitter system? Anyone? The structure is fixed, yes, but is that a problem? Yes, exactly. It needs space, and it's so bulky. But now your camera is very small. Even in your mobile phone, you can have a modern camera system. So this one is not efficient because of the size. But in terms of the system, it's good. Well, it's not really good because you split the light. It means that when you split the light, it means the energy will be split as well. It means it will be dimmer. But this kind of dimmer things can be manipulated by software. But anyway, so yeah, the main problem is because of the bulkiness. And this is actually what we have now. What we have nowadays, to compromise all the problem or to solve all the problem that we have, we use Bayer's filters. What is Bayer filters? Bayer filters means that this one cell here is one CCD, 1 pixels basically. And the other one is another pixels. So we have blue pixels, green pixels, blue pixel, green pixels. So now in your image for 1 pixel, actually you have RGB, right? It's not just one value of channel, but you have 3 channels for 1 pixels. How can you have that? how can you have RGB for 1 pixels, even though actually in the original CCD design here, you only have 1 channel for 1 pixels? Well, you just do interpolation. So for example, the green here, green is surrounding, right? And then to get the green value for this pixel here, you just do interpolation. The same for to get the blue one, because for this red here, red pixels here, you also surrounded by blue, and blue. So you can interpolate that to get blue value. So the blue value and the green value for the red pixels actually interpolation. It's not the real value for that part, for that location. But it doesn't really matter for your pixel, your pixel resolution is very high anyway. You cannot see the difference when you do this interpolation. Right? Any questions here for Bayer filters? The techniques to combine or to interpolate the numbers is called color array demosaicing or something like that, CFA demosaicing. Okay, so if there's no questions, then now if you look at your cameras, if you have multiple cameras, in this case, we have Panasonic, we have Canon, and we have Casio, and then we take these 3 cameras outside at exactly the same time, exactly the same scene, and take the pictures. And as you can see there, although the information of the geometry are exactly the same, well, almost the same, there's something different there, right? The colors are different, the quality of the colors are different, the color profiles are different. And why is this? Why the color profiles of these 3 different cameras are different? That's because of the camera sensitivity, the array, the RGB sensitivity. So as I mentioned again, even filters, RGB filters, so if you have the filter like this or the filters like this, or even like this one, for example, they have some characteristic, they have some sensitivity. And this sensitivity in terms of the spectrum is shown here. So this one is certain camera, I think it's Sony. So this one is the blue of the Sony, look like this one, and the green look like that one, and the red look like this one. And this color profile of your camera filters are different from different brand. Even from same brand, they're somehow different from different types. So this is a manufacturer who decide this, who decide the profile of the color sensitivity of your camera, or in this case, the color filters. And even human, this is the average human sensitivity. So this is taken by someone in 1964. They take up around 30 people, and from these 30 people, they calculate the sensitivity of this RGB pixel on average. Only 30 people. So they get this kind of sensitivity. It means that if you have a blue color and the blue color happens to be, or the object happens to be in this wavelength, for example, then your blueness will not be able to capture that because your blueness only capture this range of wavelengths. Okay, so that's the idea. So, and we know that different people actually have different spectral sensitivities. It means what? It means that this distribution of blue for person A and person B, they are different. So the same here. You can imagine that this is person A, this is person B. And what is the implication of this? What is the implication of this? Different people have different sensitivity. Anyone? It's the same effects when you have this. It means what? It means that your blueness and the blueness of the person next to you are different. What you think as a red is different redness from the next person, from the person next to you. Okay, so again, when we talk about colors, colors are not real thing. Colors are only in your brain. Okay, so in this world, There is no colors. It's only spectrum, energy. And it becomes colorful. Well, colorful here in the RGB is because our filters, RGB filters, because of these filters here. And these filters, the distribution of the sensitivity of these filters are different from different persons. I don't really know if you remember there is a problem of cone. There is a cone that look like silver for someone, so some people, and blue for other people, right? So I'm not really sure if you, at that time of the debate, it's called cone colors, silver or blue, right? This one, right? So this one, for what color is that? It seems to me like a gold, but some people see it as a blue. Actually, the correct one is blue. The correct one is blue. The correct one is this one. Yes, but because of the lighting, we do not know. We cannot see the lighting. That's why we can be wrong. But some people split. Some say that it's gold. Some say that it's blue. Why is that? Because again, the color is only happening in our eyes, individually different. So if it is at the boundary, then it will be difficult for a person to decide, or for people to have the same perception. Okay. So this is the problem of color constancy, the same problem, because of this spectrum, of this sensitivity, because one person's sensitivity is not the same as the other person's sensitivity. Now, we have RGB in our eyes normally. Normally, if you are normal eyes, normal people with normal eyes, then you have 3 RGB filters. But there are some people that have less. And this is called color blindness. And color blindness means what? Color blindness means that you only have 2 or 1. Means that you cannot differentiate a certain colors. If this red is gone, you cannot see red, for example. Right? So that's color blindness. Now, because there is a color blindness, means that you have only 1 or 2. On the opposite, there is also some people that have more than 3. So some people, very small number of people, can also have more than 3 sensitivities, 3 color channels. What does it mean for them? What does it mean for them if they, or if, imagine that you have 4 color sensitivities instead of 3. What happened then to you? Anyone? Well, your world will be more colorful, literally. Right? It means what? It means that most of us will see that this is white, just full white. But for that, those people, they can see something else. They see more color. Right? So that's the idea of, if you have more color sensitivity, your imagery will be more colorful. But most of us have only 3. Okay, so aside from this color sensitivity, another properties of camera is called gamma function. So in terms of the energy, so the y-axis, the y-axis is the light, the energy. The x-axis is actually the pixel value. So the correlation between the energy and the pixel values is actually linear. All devices and CCD camera, they can be calibrated so that it can be linear. But you don't like it. People don't like it. And that's why the company, the manufacturer, they change the correlation between the light and the pixel values to become non-linear. And this non-linearity of the correlation between energy that coming to the camera and the output of the pixel values is called gamma function or camera response function. I can give you the example here why people don't like it. So if the gamma function is 1, which is totally linear, the range of the pixel value will not be that much. It will be very dark in some places and quickly become very bright in the other places. So you cannot see in between. Why is that? Because the energy range is from 0 in the real world, in energy terms, is from 0 to infinity. If you look at the sun, for example, you can go blind because the energy is very, very high, right? But the camera range is very small, much smaller. It's only from 0 to 255. How can you represent 0 to infinity with 0 to 255? Right? So that's why if it's linear, you cannot see much information. So that's why you have to make it non-linear, so then you can have more information. You can basically see more. So like this one, for example, if your gamma is 4, means it's very, very curved, very, very curvy, the correlation of pixel value and energy, then it will be brighter and you can see in between. Right? So the same as this one. On the left is a linear function. The quality of the image for you is very bad. Actually, this is perfect for computer vision because we don't really need the device. The camera is become like a device to measure the light. But we cannot use the camera as a device measuring light anymore because of this camera function is not linear. So be careful with this. So if you are using physics-based, or I'm not really sure if you have time to talk about physics-based computer vision. So people in physics-based computer vision will be very much careful about this because the correlation of the light and energy is not linear anymore. So you have to recalibrate this to make this linear. So anyway, for us, for human, for consumers, we want to have something more beautiful in terms of the pixel, in terms of the image quality. So that's why the manufacturer use this kind of camera response function or gamma function to make it more informative for us. But different cameras have different gamma function. Different brands have a different camera response functions. So it is purely decided by the manufacturer based on the beautiness aesthetic of the image they can produce. Okay, so overall, this is the camera pipeline. So there's many different things inside your camera here. So inside your camera here, you have lens, and then your lens will have a Bayer filters, which is getting the color of RGB, and then you get the adjustment of the intensity value, whether you want to make it brighter or darker. So there's a camera gain control there. And then you have a white balancing. This is to remove the light colors. So basically when you have very red scenes of, for example, reddish kind of room, and then you take the picture, normally the reddish color of the light will be gone. And that's because of the white balance here, right? The white balance module here. This is software-based kind of modules. And then CFA demosaicing is try to combine all these, try to do interpolation, so then in one pixel you can have RGB values. That is CFA demosaicing. And then you have a noise reduction in terms of the software or color sharpening. And then you have color space transformation, and then you have tone reproduction to transform from one space of color to another space of color. I will not explain that one, but there is another kind of color management, so then it can suitable to your device when you display it on your screen or on your paper. And then you have a JPEG compression, and then it is stored in your file. So there's a lot of steps actually in this pipeline when you get your JPEG image. All right, so we will not go deep into this, but at least you have to know that there is some processes, some modules inside your camera. Any question here for the camera pipeline? Yes. Yes, a lot. So, for example, when you take a picture, to exactly the same object, for example, but you use a different cameras or different settings, then you will have a different quality of pixels. So you cannot trust your pixel values. So normally what we do in computer vision, we don't really use the raw pixel values. We have to transform that from these pixel values into features. So which is what's called features. So and these features will be independent from your cameras. So regardless whether your camera brand A or brand B that give you different pixel values, the features have to be the same. And that's something that we will learn in this course, how we can extract the features from different values, possible values of pixels. Does that answer your questions? Okay, good. Any other questions? Okay, so if there is no questions, I think that's all. This is just a camera demosaicing process. As I mentioned, it's just interpolation. And this is a raw image. Raw image is actually there. It's like a negative in the old day when you use film, there's a negative film. So negative film in a digital camera is called raw image. So it is not exactly negative image, but you can assume like that because raw will be, most of the raw images are linear to the energy. So it is pre-processed, right? And that raw sometimes can have more information. So that's called raw image. Any question on raw images? So it is there actually when you take a camera before being JPEG, there is a raw version. So the raw version is not aesthetic for humans because it's linear, mostly linear to the energy of the light. Okay, so in terms of the camera distortion, there are many different types of distortion. In this case, vignetting. Vignetting means that you have this kind of effects on the surrounding. Why there's effect in the surrounding like this is because your camera is like a chamber. So different lens, for example, will block some light. And in this case, A will be all of them will be captured, but for point B, some of the energy will be blocked. So that's why in the corner here, at the corner here, it will be darker because of the blocking of the lens and the construction of the chamber inside the camera. Another important distortion is called chromatic aberration. Chromatic aberration is that when you zoom in into your camera and your image, then you will have this kind of red or bluish or greenish effects. So this one is called chromatic aberration. And this chromatic aberration is because your lens have different refractive index for different light. So this light wavelength, for different wavelength, the refractive index, I'm not sure if you know about refractive index, index of refraction. If you don't worry, you can just look at Wikipedia if you want to know. It will not be tested, so it's fine. But if you know about refractive index, this is the reason of the aberration. For different bands of energy, because of the different refractive index of different wavelengths, then it will reflect refract the light differently. It is a physical limit, so you cannot do anything with this. So that's why for one pixel here, it will not receive all the lights, all the spectrum of the light. And that's the reason of the aberration, chromatic aberration. It's everywhere, including your camera. But because of the software manipulation, they try to remove this chromatic aberration from your camera. Right? But it is kind of a useful fact, because when you want to know the forgery, for example, image forgery, so this kind of chromatic aberration characteristic can be used for forensics, for image forensic. Right? So this is actually useful again for image forensic, because this is really the characteristic of the camera. It's a fingerprint of the camera. So that's called chromatic aberration. Another is a dark noise. Dark noise is an important thing here. So normally your images always have noise. The question is why. So even if you can try at home, you close your camera and take picture once you close. Even if you close, when you close your lens, what is your expectation with respect to the pixel values? Will be dark. Dark here is what value will be? 0. Right? When you close this one, you take picture, then you expect that the pixel values will be 0. But it's actually not 0. Actually, there's something like this called dark noise. And why is that? Why you have this dark noise? What is the reason that you have a dark noise? What happened with your camera? Why they give you dark noise? Because of the heat. Your camera has a battery, and the battery gives you hits, and the hits will affect your CCD, the sensitivity of your CCD. So that's why even though there's no light, there's no energy coming, your CCD still have energy sources from the heat of the camera. And that's why it's become noisy, because the heat will not distribute it uniformly across different pixels, different CCDs. So that's the reasons whenever that your image always have dark noise, because this dark noise will not disappear. It's always there. And it will be much more severe if you have low light. For example, like a nighttime. In the nighttime, if you compare the nighttime and the daytime, in terms of the noise level, the daytime will be less. You cannot see that much because the pixel signals, the real signals value is very high. But in the night, in the low light condition, the true signals, the original signal is already low. And on top of that, you have noise. So the noise will be dominant. And that's why in the nighttime, most cases, if you don't do any manipulation, then it will be very noisy. And some manufacturers try to reduce this noise by software. But in terms of the hardware, it's always there. Okay. Okay, so there is a dark noise. Another one is called saturation and blooming. Saturation is when the light is so bright and you don't use the shutter speed in a quick way. So the shutter speed is a bit slow and the light is very bright. That's why you can have the saturation. Saturation means that your CCD can receive much more energy and it go beyond 255. But there is no such a thing beyond 255. So that they stay at 255. And this 255 means there's no information because actually the information is beyond 255. And that's called, this kind of situation is called saturation. So this one, for example, here, we cannot have any information because it's saturated. And that is one CCD receive a lot of energy, right? And then the energy will spill out because it's heat, right? It's hot and this CCD will become emitter of heat. And because it's the emitter of heat, it will affect the next CCD, the next cell next to it. And this next cell actually doesn't receive a lot of energy, but because of the heat from the surrounding CCD cells, then it becomes the energy that from the neighbors from the next CCD will spill out to that CCD. And this kind of phenomenon is called blooming. So this one, for example, here, surrounding the very high intensity, surrounding here, the pixel values is also affected by the saturated pixels. And this is called blooming. All right, so there's another distortion, and another distortion is a lens flare. This is an example of lens flare, and lens flare is because of the interreflection inside the chamber. So inside the chamber, so this is your camera chamber here. So if you pay attention on the blue light here, the blue light going through the lens and then it's reflected somehow because it's always reflected by the lens, and then it goes astray from the path. So the path is actually the one here, but because it's go astray, then it will go here. And this one is called flare. It is causing the flare effects. Okay, so this is the problem of lens flare. Any questions here? Another problem in geometry is called radial distortion. So this is because of the lens characteristic. It makes the straight line like a round line. Okay, anyway, so all this is the basic knowledge on the image formation. You need to know because that will something that you have to deal with. in computer vision. Okay, so before we take a break, any questions here? All right, so if there's no question, let's take a break around 15 minutes. So let's start again for the second session at 5 minutes past 8. Okay, 5 minutes past 8, we start the second session. Thank you, everyone. All right, so let's start our second session. So we learned already about computer vision in general. We learned about image formation, and now let's deep dive into these face detection algorithms or problems. So face detections, as you can see here, the purpose of this algorithm is to find or to locate faces. So in this case, the man here, the boy, the girl, and the lady. So we want to find the location of the faces by putting this called bounding boxes. And so that's the goal of this face detection algorithms. Given an input image, we want to find the face in any given scales and in any location. So how we can have an algorithm that can handle this kind of problem? Now, please keep in mind that we are dealing with pixel values here, right? It means that the input that we have are all numbers, and how we can make sense these numbers. That's something that we have to keep in mind. So whatever the computer sees, so you have to put your brain or your imaginations as you yourself as a computers. So the computers will not be able to see like what humans see. So humans see immediately faces immediately, right? So the man, the boys, and so on. But computers don't see in that way. Computers only see numbers. So now the question is that how we can recognize faces, the location of the faces from the numbers that we have as inputs. Right. So in order to process these numbers and try to understand the meaning behind these numbers, we rely on machine learning algorithm. So the basic idea of face detection here will follow the framework of machine learning. So machine learning framework, ML frameworks, and can be split into two things, right? Two stages. One is training stage, and the other is testing stage. So in the training stage, let's assume that this one is supervised learning. So in the supervised learning, the training stage inputs will be what in this case? If you have a problem of face detection, what will be the input? Anyone? It's an image, right? Image is the input in the training stage, or images here. And what else? What else? The labels. What the labels here means? The bounding boxes. Yes. I put the labels in general for machine learning framework. And what will be the output here for the training stage? Yeah, this is the model parameters. So that's the basic idea of the training stage, the input and the output. We have images and labels, and the output will be the model parameters. If you don't understand the model parameters meaning here, it's fine. I will give you the exact example later on. Okay, so that's the training stage. In the testing stage, we also have input. What are the inputs here? Yeah, image or test image or query image, test image or query image. That's all? Yes, it's model parameters. Model parameters. So this model parameters are taken from here. It's exactly the same thing. And the output of this testing stage will be what? Yes, label, in this case, bounding boxes. Labels are, in this case, will be the bounding boxes. So that is the basic framework. We have training and testing. And maybe many of you, I think, also taking pattern recognition class. So the difference between this computer vision and pattern recognitions is that we have something specific to computer vision, which is not in machine learning. And in this case, the most important things in the process of computer vision is to extract features, or called feature extraction step. So what does it mean by feature extraction? Feature extraction is, in this case, will means that we want to transform. So basically, feature extraction is a transformation. Transformation from what to what? So we have a transformation here. So in the transformation, we have input, of course, and the output. So what is the input for the transformation of the feature extraction? What is the input? This one will be images, yes, image or pixel values. Pixel values. The intensity values from 0 to 255. And from these pixel values, we want to transform into what is called features. So we will learn later on what exact features that we want. So basically, features is the most important information that we want to capture. And this information should be invariant to the condition of the lighting, the condition of the camera, and so on. So even if you have different cameras, even if you have different lighting conditions, these features have to be the same for the same object. So that's the basic idea of features. It have to be invariant. So the features have to be invariant to any changes surrounding the object, any changes surrounding the object. So I put it outside the object. So if the object itself is changing, then of course the feature will have to change. But outside, invariant to any changes outside the object itself. Right, so that's the basic idea of the features. So regardless what type of cameras you have, regardless the situation of the lighting, if the object is the same, then the features have to be the same. So that's the basic notion of the basic meaning of features. Any questions here? So in these object detection algorithms, we will learn certain techniques, and this technique is called Viola Jones. So Viola Jones is the inventor of the algorithm. So Viola Jones phase detection. In Viola Jones in phase detection, there are two basic components here. Two basic components. And these two basic components, one is features or feature extraction, and the other is classification. Right? So that's something that we want to learn further, how we can extract features that invariant into any changes outside the object itself, and how we can classify to differentiate between phases and non-phases. And to differentiate between phase and non-phase is called classification. Right, any questions so far? So to get this feature extraction, we need to know about something basic in computer vision, which is called image convolution. How many of you know about image convolution already? 1, 2, 3. Oh, many of you. Okay, so that's good. But many of you also don't know about this image convolution, so I will explain a bit quickly. Right, so let's look at image convolution here. Or in convolution in general first. Convolution. Convolutions, the purpose of image convolution is the feature extraction normally. Not always, but feature extraction rely on image convolution a lot. So convolution in 1D is 1D convolution is very straightforward. When I say straightforward in terms of the mathematics of the analog, in analog it will be f convolved with g with respect to a variable x is defined as the integral of f u g x minus u du. So this is the definition of convolution in analog. But we don't use analog actually in computer vision. We use discrete version of this. The discrete version is the same as convolved with g with respect to variable x equals to sum of u equals to minus infinity to plus infinity fu g x minus u. So this is the definition of convolution in discrete. But what it means by this, right? The meaning behind this operation is the most important thing. It means that, for example, here, if f, assume f is the kernel. So f is the kernel. So fx is the kernel, or f itself is the kernel. Okay, the kernel is something that the filters or kernel here is our filters that you want to apply to the input data. So the kernels assume that we have factors 3 by 1. Right. So in this case, we have u here, the index of the factors, and u here is plus 1, 0, minus 1, for example. Right. It's up to you to have the index as long as it agree with the definition. It's fine. So and assume that we have the value inside these vectors of the kernel is 1 to 3. So 1 to 3 is the values of your kernel. And then you have gx. Gx is your input signals. And in your input signals, it's very long signals, but I will just take a few of them. Right, so assume that you have 5, 10, 7, 0, for example. This is your signals. Right, so in this case, you also have the index. In this case, your index x. And your x, if you have 1, 2, 3, 4, 5, and so on. So we start from 1 here. And now, when we say that f convolved with g, we say that f convolved with g when x equals to when u actually let me think. So x here, sorry. So x here is the location. So x is 2. So x is 2 means that we are dealing with this one. So we are dealing with this. X equals to 2. Right. So assume that we want to know the output is, of course, another one. The output, so let's say the output is h, for example, h of x, right? So the output is h here, another factors. And this is index x, 1, 2, 3, 4, 5. And then we want to know what will be the value at that location. So that's why this is 2 here. We want to know what is the value of the output at that location. Right. So in this case, we simply multiply 1 with, we multiply 1 with 1. Anyone? Or we want multiply. What is the result here? For those who know already the operation of convolution. So we put this one, we take this one, we take this one on top of this. So we put like that, we map them, right? In that case, 1 will map to 5, 2 will map to 10, and 3 will map to 7. So we write 1 multiplied by 5 plus 10 multiplied by 2 plus 3 multiplied by 7. And this will give you the value of 46. And that's the value of 46 that you have to write there. That when the value of x equals to 2. Now let's have another example. F convolved with x, and x we want is 3. So we want to get the value here, the output at that location. So in that case, we map this one, this kernel here, move one cell. So we move that here. So now 1 map with 10, 2 map with 7, 3 map with 0. So what we have to write is that 1 multiplied by 10 plus 2 multiplied by 7 plus 3 multiplied by 0. And this case you get 24. So this is 24. So you do this all over the data. So that's why it's called kernel, because the kernel will try to map for all the place there that you want to convolve. Any questions here? It's very straightforward, I think, right? Okay, so that's 1D convolution. We also have 2D convolution. The basic idea of 2D convolution is exactly the same. Again, by definition in discrete, we have F convolved with G, for the index x and y. And this one is sum over V equal to minus infinity plus infinity, and sum over U minus infinity plus infinity. And this is FUV multiplied by G, x minus U, y minus V. So that's the definition of 2D. But the operation is exactly the same. So normally we don't use F in computer vision, or in many different fields as well. We just call, well, F is sometimes used because F stands for filters. But we also use K, which stands for kernel, for F. So anyway, regardless of whether it's F or K, we have two-dimensional kernel or two-dimensional filters. And let's assume that we have -1, -2, -1, 0, 0, 0 for this kernel. And then you have an input image. For example, your input image is a logic matrix. Now, you have a value, of course, for this every cells. And if you want to know, you convolve this. And if you want to know the value of this one, for example, if you want to know the value of that one, the value of this one here, what is the output of that one? So you have this number here. The numbers here is, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. I just made up this number here, right? Whatever you have a number here. So in this case, if you want to know the location of this value here, you just map that one, map this kernel into this location here. And then by multiplying this exactly with the same mechanisms, you will get the value then. All right. So this is 2D convolution. If you want to know the value for this one, for example, for this location here, the blue location there, if you want to know that one, then you have to convolve your filters with this location here. You have to shift. In that case, you will get, after the convolution, you will get that value there. Okay, so that one will be the 2D operation of the convolutions. Any questions for the operation? Yeah.
The rows of the X will always be.
Sorry again?
So one of the rows of the X will always be.
That's correct. So this location here will have no operation, will not have no values, because there is not possible way to map on that location, right? If you try to map that one, what happens is that if you try to map, you will map in this way. To get this value there, you have to map in this way, right? And there is no value here. So that's why you cannot have that edges, the value at edges. In computer vision, you can ignore the edges basically in most cases. But if you want to have the value, is there any trick that you can do? Yes, it's called padding. Padding means that you just made up a value there, either copying the edges values or you just put 0. If you put 0, then you can do the operation. Although the value in the screen, in the yellow area, will not be correct because actually there is no information. Okay. Any questions here? Right, so that is called padding. The operation is called padding. In this case, I used 0. It means 0 padding. There's a lot of different ways to do the padding, but 0 padding is the popular one. Any other questions here, everyone? So this is very basic. You need to understand this. Actually, this one is something to do, if you learn about deep learning later on, has something to do with CNN. CNN stand for convolutional neural network. And convolutional neural network operation is exactly this one. Right? So you have to understand that. To understand this operation is very, very important, not only in computer vision, but many different fields in AI. Again, if you don't understand, please ask. Any questions for this convolution operation? Maybe some of you have a question in mind, what is the meaning of all this, right? What is the implication of this operation? I understand the mechanic behind this, how to compute the convolution output, but what's the meaning of this? Why this is interesting? Why this is so important? Well, this is important because features in computer vision at least, or actually in natural language processing as well, can be extracted with this operation. So this has something to do with feature extraction. And why this has something to do with feature extraction, we will see that later on. But as a primary information, you can see that if you change your kernel, here, you will have different output. Even though you have the same input, this is input, even though you have the same input, but if you have different kernel, you will have different output. So the kernel, depending on what you want, will give you something. So for example, if you want to get edges here, you have an image and then you try to find the edges. the skeleton or the contour of the objects. So in that case, what kind of kernel that you have to apply? Not Gaussian. I want to have edges. The simplest one will be what? Anyone? How many of you have taken image processing course? None of you. Well, you need to apply the basic one. There's a lot of different ways, different filters, different kernels to give you edges, but the basic one is called Sobel. Sobel operators or Sobel kernel. So I can give you an example here. Sobel kernel. Sobel. So this is Sobel kernels. So this is the kernels. So that's the kernels. Minus one, minus two on the left, plus one, plus two, plus one in the right, and 0 in the middle for the horizontal line. For the vertical line, you have gy there. Gx is for the vertical line, gy for horizontal line. Is that the other way around? I think the other way around. Gx is actually the horizontal, gy is actually for the vertical. Anyway, so this is the kernel. So now, what is the input and the output? So this is the input and the output. So the original is the input there, right? On the top left is the input. On the bottom left is Sobel X. I think that one is taken from GX. Then you can get that kind of line. And then for Sobel Y, you will have the other one. If you combine Sobel X and Sobel Y, you will have the full edges. So depending on the kernels, you will have this kind of outputs. Don't bother about the Laplacian, the top right. We will learn that perhaps later on. Okay. So that's called Sobel kernel. When you do the operation of convolution with the Sobel kernel, your image will become edges. Now, that's if you use Sobel, you get edges. And what happens if you use, as mentioned already here, Gaussian kernel? What kind of output that you will have? Yes, it's a blurry image. So let's look at the Gaussian kernel example. So Gaussian kernels looks like Gaussian. So this is the analog version. This is a Gaussian shape. But of course, this is analog. So how we can change that into discrete, right? So if you look at the discrete version, so this one in the middle, so the one in the middle here is high, and then something in the periphery will be smaller and smaller, look like Gaussian. So it will be more obvious if you look at the larger kernel. So this is a very large kernel, and then you see here is very high, and then gradually smaller and smaller. And if you draw this into a diagram or draw this into a figures, then it will look like a Gaussian, discrete Gaussians, right? So that's how the Gaussian kernels look like. Now, what will be the effect of this? The effects of this Gaussian kernel convolution. So the effect of that, well, you see. It's not quick. Let's see, Gaussian kernel or Gaussian filters are the same thing. Right. So this is the Gaussian in analog in 1D, and this is Gaussian in 2D, and this is the kernel that, as I mentioned, is if you look this one from the top view, if you look at this one from the bird view, top view, it will look like this one. And if you do the operation on this image, for example, so let me show you in different page. And then we have a Gaussian kernel output here. So this one is the input, right? Very sharp image. And after Gaussian kernel, you will have this kind of output. So as you can see there, at the boundary, it's just dark black, because there's no information at the boundary. Right? Any questions here? So that's how you can get the outputs different, exactly the same operation. The convolution is exactly the same, but because of different kernels, you will have different outputs. And you can have many different kind of output here, depend on the kernel you have. And this is exactly the basic idea of CNN. CNN will try to get this value there, automatically learn from the data. So then you can have many different types of output here, whatever the output that suits to the application. Okay. Any questions for this 2D convolution? Right, so that's the basic idea of the convolutions. Next is that we need to get features, right? The features in Villa-Jones, so features used by Villa-Jones is called hard-like features. Hard-like features. So this is the features used by Villa-Jones. So this is the keyword that you need to keep in mind, hard-like features. So what is this hard-like features? So hard-like features, the thing that make features or make this convolution different is actually the kernels, right? So we have three types. In this case here, there are three types of kernel, three types of kernels. And the kernels here, in other words, is filters. So kernels or filters or mask. It's the same thing because we're masking the image, right? With one by one. So there are three types of kernels. In total, we will have 5 actually. So the type 1, type mask. So type 1 will be something like this. And so the black one has a value of 0. The black one has a value of 0. The white one have the value, the black one have a value of -1. The white one have the value of +1. So this one is -1, +1. That's type 1. Type 2 have this kind of shape. Again, the black one is a -1. So this is the second type of the mask. So actually, this is factors. So when I say this -1 and 1, your imagination for the whole computer sheet is it is -1 is +1. The same here is actually -1 +1. Okay. And type 3 is something like this. No. So there are 3 types, and in total you have 5 different masks. So in total, there are 5 masks. So that's the kernels. And how we can get the features from this kernel? That's the question, right? Okay, so we know the kernels already. And let's have an example of convolution with the kernel. So the convolution of the kernel, first you have input image I, and assume that this is a grayscale. Assume this is grayscale. And then you have very big image. Right? And let's assume that you have a value here 100 and the value next to it 150. That's your grayscale pixel value. And if you use type 1, and if you use this kernel here, right, means that we have to get mask on top of these pixels. You map that one. So again, the black one is -1. So this one is actually -1, and this one is +1. You do the convolution between +1 and -1 with 150 and 100. So what is the outcome of this operation? So in this case, you have features 1, just call it the feature 1, because we convolve one mask at that location and call it feature 1. And the feature 1, based on the convolution operation, will give you what? What will be the value that you will get? Anyone? What the value that you will get here? This will be 50. That's correct. 50, because -1 multiplied by 100 plus +1 multiplied by 150 give you 50. Okay, so that's the operation for the convolution. And of course, for F2, that one is F1. So if you have F2, you want to have this one, for example. That will be F2. Regardless whether F2 will be this one, it's really up to you. But let's stick with that one. That one for F2. So F2 exactly the same operation, right? And this is the operation that you have to do for every pixels. So you have to have scan operation for every windows. So you have to slide the windows all along the pixels. So you have to slide this, or slide in this way is fine. For the mask 1. So in that case, you have many of these F3, F4, until many of them. And you store this F into what we call descriptors. So we store that into descriptors. So your descriptor F will have long factors. And this value here will be 50 because it is F1. So this one is F1. And next to it is F2, whatever F2 value that you have here. And the next there, F3, and so on and so forth. That only for the type 1 mask. That's only for this mask here. So for that mask, you have to slide all the way, and then you will have maybe the value up to this point there. That will be type 1 mask when convolved with all pixels in your image. Any questions? This is important. If you don't understand, please ask. Yes. Yeah.
Second, if you do the, I'm wondering if you too many chances of input and the backup, since the output is also one dimensional.
You can, whatever the things you want to do is fine. Whether you want to find in this way, right, in that direction, or you want to find you do it in this way. It's up to you. But you have to stick with one operation, but stick with one way of doing. If you have this, you have to do it for all the rest of your operation. Okay, so it doesn't really matter actually which way you want to do. Does it answer your question? Okay. Again, if you don't understand, please ask, because this one is important. We will move along bit by bit because this kind of understanding. If you don't understand this, you will get lost. Any other questions? Okay, so if there's no questions, so that's step one. So you do the same thing for this one, for the second mouse, for the same type but the mouse. So you want to do this also for that one is vertical, and you do this for all the rows as well. It's up to you how you want to do it, but you have to stick to that kind of ways. And that also give you a value. Maybe from that one is this is mask 1, this is mask 2. Many of them. It's not just 3 or 2, but many of them. Okay. Any questions for this mask 2? Once you finish with mask number 2, you then move on exactly the same operation for mask number 3. So assume that this one is mask number 3, M3. So now you have 3 pixels in the operation. And you store there also here, M3. Okay. So you have M1, M2, and 3 outputs. You do the same for all the masks here, M4 and M5. And you store that into these long factors here. Again, this is called descriptors. So there are 2 keywords so far, or 3 maybe: convolution, features, and descriptors. Descriptors is always vectors. All right, so what is the difference between features and descriptors? Anyone can answer? What is the difference between features and descriptors? Well, there is not much different. Basically, descriptors is a vector of features. So this one is called, this is your features. F1, F2, F3, and so on are your features. And the descriptors is the vectors of your features. Okay, so again, descriptors is the vector of features. Yes.
So the descriptor is five layer
Factors. No, it's not 5 layers. It's just 1 factors. Yeah, we just concatenate the features. Concatenate means that you put behind bit by bit. So M1 is actually take up that factors, and then you add M2, this is M1, this M2, and this one is M3, and so on. You concatenate the factors. Yeah, good question. Any other questions? Right. So now, not only that you have to do in that way, not only that you need to do in that way, but you also need to increase your mask. So what it means by that? So once you have done for all the features, for the type 1, for example, mask 1, you need to increase this. the original size of the mask is 1/2, right? So this one is actually 1/2. You scale this up into 2/4. You scale this up. And once you scale that mask up, then you need to map this now 2/4, 2/4. Then you have to do the operation on top of that 2/4 pixels. Is that understandable? So not only just the original size of the mask, but you need to scale up the mask and do the convolution again. And that also need to be added here to be concatenated there. Okay. So you do this for all pixels as well. So you have to shift this. So you have to shift that for all pixels as well. Once you have done that, you need to scale that mask again. You have to scale this mask again 3/6. And you do exactly the same operation and concatenate the value to the descriptors. Okay. You have to do this as many as you can, as long as it can map to your input. And actually, are there any questions here? You don't do this scaling up the mask for M1, for mask 1, but you have to do it for all masks. Okay. So these factors, the descriptors here is very, very long. And actually in the Villa-Jones algorithms, your input here, your training input data, your input grayscale here, grayscale input data, grayscale input image data for training is the size of the image is 24/24. So I is 24/24 pixels. So when you scale up your mask, it is constrained by this 24/24. So your mask cannot go beyond 24/24. If it is already go beyond 24/24, you stop. Okay, so the 24/24 is the maximum mask that you can scale up. Is that understandable? So it will not go beyond 24/24 in any meanings. So because your kernel is not square, your kernel is some of them, many of them actually rectangular. So when the rectangular already some of the side of the rectangular beyond 24/24, you have to stop. It cannot go beyond 24/24. And if you do this for all masks, the length of your descriptors, here will be 160K. 160,000 features. Any questions here? So I can give you the idea of the operation. So this is the mask that we learned. And this is the example of positive samples. So the positive samples will be 24/24 images. So one of these, for example, this pixels, this image here, it is 24/24 resolution. It's very small. 24/24 is very small in terms of the pixels. So the resolution is not that high. Right? So why this is 160,000? Why this 160K? Because when you do the counting, so this one is the input 24/24. you have 5 masks, right? And this is the mask M1, M2, M3, M4, M5. So you have, oh, that means 5 minutes left. Right, so that's how you can get, if you count this, then it will be 160K. If you do all the loops here, it's 160K. Please look at the source code and see if you can understand why you can get 160K. Okay. Any questions here? So that's how you can get the descriptors. So one image here, you will have 160K features. Means that you will have one descriptors. So one descriptors with a length of 160K will represent one image. Will represent 24 by 24 image. And actually, that's how you can get the features. That is the extraction of the features. So again, this is the operation of convolution 24 by 24. You convolve in many different ways, scaling up the mask for all pixels, then you can get the features. Now, let's have this few minutes to discuss what is the essence of this. Why this is important, why this can work, why this can handle different types of light intensities. Some of them is actually brighter than the others. But why these features can represent all these different images? Any answer for that? Well, as I mentioned again, the features that we have here, for example, that one. Let's not that one, that two, for example. That two is very similar to what? Very similar to Sobel. Yeah, very similar to Sobel operator that I just mentioned. Sobel operator is negative on the side, 0, and then positive, right? So this kind of operation, 1 minus 1, positive 1 minus 1 positive, will give you edges. Right? And this one, actually, if you look at the kernel operation, it looks like what kind of operation is this? Minus 1 here and positive 1 here. If you do the convolution, what kind of operation in mathematics that represents for? Is it? It is the, sorry again? The difference between 2 pixels, and that mathematically is called what? It's called derivative. Exactly. So this one is actually represents the derivative in the x direction. Derivative in x direction. And the other one, this one here, is derivative in the y direction. And derivative is very important in the image because derivative, another name of derivative in computer vision is called gradients. So this one is the same thing like gradient. So the type 1 of the mask is actually gradient information, derivative information. Type 2 will be look like a Sobel, will give you the edges, and type 3, I think, can give you corners. Okay, so all this is because of the type of the type of the kernels that we have here that can give you independent information regardless the intensity of your input image. It doesn't care because the gradient will remove out the absolute intensity values and only consider the difference between the pixels. So we will discuss this again next week. So before we end this lecture today, are there any questions? Yes.
You take the description, the console is the first row, a person for also a computer, but in the previous we show the The first row and the first always there that all of the
Yeah, that's true. The one that I just mentioned to you in the example here, in the beginning of this example here, because I use this kind of kernels. This kernel is 3 by 3. So if 3 by 3, the corners are here, the corners on the brown color there will not, we will have no information. So in the end, the first column will not have information. This column here will not have any information, right? But in our kernels now, it's not the same. The kernel is only 1 by 2. So 1 by 2, of course, in the kernel, if you put the mask here, for example, if you put the mask here, you will not have any value there. So we avoid that one. We start from here, from this. So in the end, in the last part, here, you will never compute this one. You will lose the information. But that's fine. Don't worry about that. It's only just very small boundary problem. Okay. Any other questions? Yes.
For 160K features,
Yeah.
you have the same amount of filters accordingly or accordingly by.
You have to scale up every one of them. Yeah. Scale up not only just 1 time, but 2 times, 3 times, 4 times, 6 times, as long as it can be inside the input image.
So you end up with having the same amount of filters.
The same amount of filters
You want to have 160K
for one image. For one image, we will have 160K. 160K output of the convolution. Yeah.
So you need value.
So 160K will be the value. Yeah. So this one will be a factor value. Factor is a mathematical representation of value. Right? Okay, good. Any other questions? Yes.
For each vehicle, you have resolution or data.
Oh yeah. As I mentioned again, it is a grayscale. So this one we consider the input grayscale. Is as I mentioned in this example here, it's also grayscale. We don't really consider color in these algorithms. Yeah, good questions. Any other questions? If no questions, then that's all today. Thank you, everyone, and see you next week again. Thank you. Thank you.